Welcome back, Mr. Wakefield here, looking at section 5.2, and in these next two sections, both this one and in the next video where we'll look at 5.3, we're going to be doing something called systems of linear equations. And what we do is we take two equations, we put them together, and I want to make it clear right off the bat here. I know that this problem, if you don't look at the directions, you just look at the problem, it looks like that problem that we did back in chapter 4 where I asked you if it was parallel, perpendicular, or neither. Okay, that is not what this problem is. It looks similar, right? But because the directions say something different, it has nothing to do with parallel, perpendicular, or neither here. It just says to solve the system. Okay, when that happens, let's talk about what that means. Okay, first of all, what that means is when you solve a system and they give you two equations, they want you to find the answer or answers that make both of the equations true. Okay, whatever is a solution to this one, in other words, and also a solution to this one, has to be a solution to both of them in order to be in the final answer. Okay. From a graphing perspective, because remember, these equations, don't they look like the kind of things that you would graph a line with? In fact, I'll remind you of that from chapter 4. See how those two equations look like the kind of equations we graphed in chapter 4? That's not a coincidence, okay? When you have a polynomial on both sides of the equal sign and you just have x to the first and y to the first, no x squares or y squares, again, that's going to be a line, okay, when you graph it. And so both of these things, if I were to graph them, would be lines. And let me make something clear here, you guys. We are not going to be graphing these problems in this section. This is just something to kind of help you understand the problem a little bit better. But we're not actually going to have to graph when we actually solve it. But this will help you understand what the purpose of the problem is a little bit more, and that just makes it easier for you. So let's just, I don't know exactly what these graphs look like, but let's just say, for example, that first line, and it's not important what they look like, okay? We're not trying to graph here. This is just something to help you. But let's just pretend that this equation right here, if I graphed it, it looked like this right here. And let's put my arrows on there. Now remember, you guys, we learned in chapter 4 that when you graph a line, that line contains all of the solutions to the equation that it came from. So that means that all the points on this line right here are solutions to that first equation. Okay? Now, let's say that the second equation here, again, just speculating here, all right? This is not necessarily the real graph, but that's not important here. Let's just say that this graph looks something like this, okay? That means that this second line right here, and notice I put both of the lines on the same graph. I don't normally do that, right? Normally we wouldn't do that, but we are going to do that here again just to help you understand what's going on with this problem, the purpose of it, okay? This right here, this second equation, represents this line right here. That means that all of the points on this line right here, all the points that are contained on the line are solutions to that second equation. So let's review here. The first line, the one that's a little bit more flat here, all of the points on there are solutions to the first equation, right? And all the points that are on this second line right here are solutions to the second equation. Remember what I said that we needed to do? We needed to find the answer that makes both of the equations true, that's a solution to both equations, in other words. Okay, so if all the solutions to the first equation are on this line, and if all the solutions to the second equation are on this line, is there any points that are solutions to both of them, both of the equations? Okay, well, wouldn't that, in order to be a solution to both equations, wouldn't that point have to be on both lines? Because the lines are where the solutions are located. So if you have a point that's on both lines, that means it's a solution to both equations, and then that's what the solution to this system is going to be right here. Okay, well, isn't this point right here where the two lines intersect, isn't that point right there the solution? Because it's the one point and the only point that's on both lines. And so that point right there is going to be the answer. And you might be wondering, well, what point is that? It looks kind of like it could be 1, 0 or 2, 0 or something close to that. Okay, yeah, it looks like that. But again, we're not actually going to use graphs to figure this out in this section. All right, we are just again looking at the graphs to help us understand where the answers come from, basically. To actually find out the actual answer, we're going to do a different method in this section, and then yet a different method after that in the next section. All right, but graphing, again, gives us a good illustration of what's going on. Okay, so if you're a visual learner, that helps as well. Helps you understand it. Anyway, so that's what happens in most of these problems, is that the two lines intersect each other, and then you get this one answer. Okay, but it's a lot easier to find the answer by using other methods other than graphing, because drawing graphs, as you know, is not necessarily a perfect science. Okay, it's hard to make your graphs come out exactly in the exact perfect spot that they're supposed to come. Okay, even if you're good at drawing straight lines, it's still not necessarily easy to get a perfect exact answer. So we're going to go about it a different way, but you can see that there should be an answer here, okay, and it would be at the intersection point. All right, we're going to look back at graphs here in a little bit as we see different types of answers, because here's the thing, you guys. Not every answer is going to have not every problem, is going to have just one answer, okay? And we'll look at that as we go along here, but most of them will, including this one right here. So how do we actually figure out what this one point is that's a solution to both equations? How do we figure that thing out? Let's learn right now. The method we're going to look at in this section is called the substitution method. It's a 5-step process. Okay. The first step says choose one of the equations, your choice, and solve for one of the variables. So in other words, that means, you guys, that we have a choice of any one of the 4 variables right here. Any one of these 4 variables, you need to solve for it. And what does that mean again? That means to get the variable by itself, right? So that it also isn't on the other side of the equal sign too. Okay. Now we saw that in section 4.4 when we had 2 variables in our equation and we had to get the y by itself so that you could get it into the y equal to mx plus b form. Okay, and we did the slope and the intercept, the m and the b. Okay, how did we get the y by itself there? Not that you have to get y by itself in the current section that we're working on, but this will help even if you're getting x by itself. What we did was we got the term that had the variable in it by itself, get the entire term by itself that has a variable in it. Okay, and I did that by moving the 2x over here. And then once you get the term that has y in it by itself, you then divide out to get the y completely by itself. We're going to do that same exact thing in the current section here, all right? But again, you don't have to do y. You could pick one of the x's as well. In fact, what I would highly recommend to you is that since you have a choice of any one of these 4 here that I circled, pick one of the terms that has either a positive 1 in front of the variable or a negative 1 in front of the variable. Okay, see how this is 1x right here because it's invisible? Okay, there's an invisible 1 there. So that's usually going to be the easiest one. If you pick one of these other ones, you guys, you're going to end up with a fraction. And since this is just the first step of the problem, we want to avoid fractions if we can. And since we got a choice here of any one of these 4 to use, why not pick the one that's not going to give us a fraction? Because, and I'll show you why that's going to end up not being a fraction here in a moment. All right, but it's mainly because you have to, in these other ones, you're going to, if I got this y by itself, I'd have to divide by 4 on the last step. If I got this y by itself, I'd have to divide by 3. If I got this x by itself, I'd have to divide by 5. But here, you don't have to divide because when the coefficient is 1, if I did divide by 1, it's not going to change anything when you divide by 1. So the division step is actually unnecessary if you get this variable by itself. So that would be the best, easiest choice. So that's what I'm going to do. I am going to, step 1 right here, I am going to take this equation and I'm going to, first of all, just like I did back in section 4.4 over here, if there's a variable I want to get by itself, all right, I get the term that has the variable in it by itself first by adding or subtracting the term that's on the same side as that term. Okay, in this case, 2x is on the same side as this term here that I want to get by itself, negative 5y. Okay, and I want to take that term and add or subtract it over to the other side. Since I want to get the x term by itself here, that means that since 4y is positive, I want to subtract it over. If it had been minus 4y, then we would add 4y over. The 4y's cancel on the left, and we get 1 minus 4y. You could also say negative 4y plus 1, all right, your choice. But it's not important here to write it in a certain order, not in this case. Step 2. Now that I've gotten a variable by itself, again, doesn't matter which of these 4 that you did, but this one obviously was the easiest one because you didn't have to divide out, okay, and you didn't end up with a fraction. So here's the very key step right here. What you got to do is you got to take this answer that you got and you need to plug it into the other equation. Very important you plug it into the other equation. So since the answer from step 1 came from the first equation, you got to plug it into the second equation. If the answer from step 1 had come from the second equation, then you'd have to plug it into the first. You always plug it into the other one on this step. All right? So therefore, we need to plug it into the second equation. All right? And how do we plug it in? What does it mean to plug an equation into another equation? Here's what we mean by that. Since x was solved for, and since it's equal to this right here, 1 minus 4y, we're going to take the x in the other equation, and we're going to replace it with 1 minus 4y. So whatever the variable ended up being equal to when you got it by itself, you take that and you plug it into the other equation and it replaces that variable. Okay. Use parentheses. Okay. Whenever you plug something into a variable, you guys know that you got to use parentheses. Right? Okay. We've done that a number of times. And that leads to this equation right here. And what's great about this equation right here as we move on to the next step is that it has only one variable in it. And we know from studying one variable linear equations, okay, that we did back in chapter 3 right here. We know that when you have a one variable linear equation, which is what this is always going to be on this step, all right, we know how to solve those. Okay, we clear the parentheses, combine like terms, move the variable terms to one side and the constants to the other, all that stuff, including the division step, which is the last step. Okay, that's what you do on this next part here after you plug it into the other equation. So I distribute. This is the third step now. Then I what? Then I combine like terms. Negative 17y. Then I have that step where I need to take the variable term and put it on the opposite side of where the other two terms are supposed to go. So that means that the 5 and the 5, since they don't have the variable in it, they need to be put on the opposite side of where the variable term is. Okay. Both of these cancel here. That means that we get, if everything cancels on one side of the equal sign here, that means that it's 0, right? When you're combining like terms on each side of the equal sign, which is what we always do when we add or subtract the same amount here to each side. Okay, so we get 0. Then it's the division step. We know that when you have a 0 on top of a fraction but a non-zero number underneath it, that means that it's equal to 0. Okay. So you might be thinking, hey, I got the variable by itself. Does that mean I'm done? No, you're not quite done yet. Okay. We just did step 3, which is to solve the equation. Step 4 now is to realize, you guys, that what? Well, when we were looking at that graph earlier, this is not just one number here. This is an ordered pair, okay? When you find a point on a graph, that's an ordered pair. An ordered pair is both a y and an x, right? Okay. In fact, this kind of looks like 1, 0, right? It might be something else, we'll see. But I'm just giving you a visual of what's going on. All right. A point is two numbers with a comma in between it, right? It's an ordered pair. And so when you find what the first variable is equal to, you're not done yet. That's just half the battle, okay? We still got to find out what the other variable is. Here's how you do it. You take that answer from the end of step 3, and you plug it into the equation that you got at the end of step 1. Okay. So since y was equal to 0, I plugged that into y here. All right, since y is equal to 0, that's perfectly legitimate to do that. And then you now have, since you already have x by itself here, you just have to figure out what this side of the equal sign is equal to, just doing order of operations. There's no variables here, so order of operations makes sense on this side of the equal sign. Negative 4 times 0 is 0. So 1 plus 0, of course, that's equal to 1. And so now I have figured out what both of the variables are equal to. Y equal to 0, x equal to 1. So that means that this point where the two lines intersected, that excuse me, that is 1, 0. Again, you don't have to do any graphing, but I'm just giving you a visual of what's going on. So the last step here, step 5, is to just simply put those two numbers together as an ordered pair. Make sure the x number always goes first, as you always do in an ordered pair. And so your final answer is 1, 0, because x is equal to 1 and y is equal to 0. Okay, and that is the one point, the one ordered pair, that if you plugged 1, 0 into both of these equations, it would make them both true. Okay, this is the point and the only point that makes them both true when you plug it in. All right, and that's why it's the only solution that you get. So therefore, we solved the system. We found the point that makes both equations true. That's a solution to both equations. Let's keep going here. Again, what's the first step? You look at your 4 variables, you guys. And which one of those 4 variables would be easiest to get by itself? Preferably one that will not give you a fraction. Okay, well, notice the coefficient of this variable right here is -1 in front, right? Just like +1 over here, if you have a coefficient of -1, that's usually a good one to pick. +1 like this one, or -1 like this one, talking about the coefficient in front of the variable, those are both good choices, 1 and -1, because the thing is that when you, and let me go and write it out first and then you'll be able to see it. But in step 1, what do we got to do if I get that y by itself? You need to, first of all, like I said, in order to get a variable by itself, when you have a polynomial on each side of the equal sign, like we will on all of these problems in this section, what you want to do is you want to first of all get the term that has the variable in it that you want to get by itself. You want to get that by itself first, and then you'll want to divide out the -1 after that. And the way that we get that term by itself is by adding or subtracting the other term that's on the same side as -y over to the other side. Since this is -2x, you want to add 2x to get this to cancel. And we get this right here. Again, it doesn't matter what order you put these two terms in here, as long as the signs are correct in front of each one. And you have a plus or minus in between, because again, they're not like terms. So you can't combine them. But what we also have to do, see, y is not by itself yet. You have to what? You have to divide out the -1, because that's -1y on the left side of the equal sign there. But here's the great news, you guys. When your coefficient is -1, if you don't already have a fraction over here before you divide by the -1, the -1 is not going to make a fraction. Because the great thing about dividing by -1 is that it just changes the sign of what you're dividing. It doesn't create a fraction that's not already there. Okay? So that's why -1 was a good choice here as far as picking the term that had a coefficient of -1. All right? Here's what happens. As we learned back in 4.4 here, when you divide by a term here, when you divide the two terms here by a single term underneath it, and that's what you got to do, you got to take this bar all the way across both terms here, all right, to indicate that you're dividing both of the terms by -1, just like I divided by 3 here. We're dividing by -1 here. And then what we learned is that you have to both of these terms individually need to be divided by this number underneath. That's when you got two terms up here with a plus or minus in between them. Okay, and then we learn that we figure out what the sign is, and we create these two new fractions, and they're not going to stay fractions. Like I promised you, we're not going to end up with fractions here, but initially it'll look like that, just like it did here when we created two fractions. Okay, let me show you that here. Positive divided by negative is negative, so that's going to be -3/1. Put the negative in front, all right? And then, again, positive divided by negative is negative, so we put the minus in front. If it had been positive, we put the plus in front, okay? Just like we did in 4.4 right here, all right? We put the correct sign in front of each fraction there. Same thing here, negative and negative, all right? But notice that both of the fractions they both have a 1 underneath it. So that means the fraction is going to go away, right? That's what happens when you divide by -1, all right? The only thing that the negative does is it affects the sign, and the sign goes in front of the fraction, and then you just have a 1 underneath it, okay? And the one's not going to keep it as a fraction. You can get rid of the 1. As we know, when you divide by 1, the 1 doesn't need to be written. So -3, don't need the 1, and then -2x. Again, you don't need the 1. So as you can see here, when you divide by -1, all right, the negative just affects the sign of each of these two terms here, and then you can get rid of the 1 after that. So no fractions. Great. Okay, what's step 2? Step 2 is where we take the answer that we got in step 1. We did the same thing in problem A over here. We take the answer that we got in step 1 and we plug it into the other equation. Since this again came from the first equation, you got to go back and plug it into the second equation. All right. How do we do that? Well, since we solved for y in the first step, we now need to plug it into the y in the next step here. Here's how it works. 3x plus 2 times, and then like I said, if you're plugging into a variable, use a parenthesis, and then you replace that y right there with what y was equal to down here, which is -3 minus 2x, like that. And then bring down that -3 in that equation. So you can see that I plugged the answer from step 1 into the other equation here. Everything stayed the same except for the fact that I replaced the y with the -3 minus 2x. What was the third step that we did in the last equation? That's where you now solve the equation that you ended up with here. There's only one variable in it, and we know how to solve one variable linear equations. We've done that many times, all right, from chapter 3 again, all right, with these 4 steps. This is for when you have a one variable linear equation. Because of the fact that I substituted on the step 2 right there, I now have just one variable in this equation. X is that variable, right? So we need to distribute. Okay, doing the same steps from the chapter 3 that I just showed you. Okay, then you combine like terms. Okay, then we what? Then we need to move over the 2 terms that don't have the variable in it so that they're on the opposite side of where the variable term is. So that means I need to move over the 6 with the -3, like that. I get negative x is equal to positive 3. Okay, but we still need to divide out. And since the coefficient is negative 1, you have to divide out. Okay. X equal to negative 3. That's step 3. Step 3, again, is to figure out what that variable is equal to. Step 4 is where you figure out what the other variable is. Okay, so since I just solved for x, now I need to figure out what y is by plugging it into, just like I did in the last problem. On step 4, you take the answer from step 3 and you plug it into that answer you got from step 1. So step 4 essentially is a combination of step 3 and step 1. Okay, same thing here. We take the answer from step 3 and we plug it into the answer from step 1. So y is equal to negative 3 minus, now be careful to plug it into the correct variable. Since it's x equal to negative 3, you got to plug it into the x, not into the y over here. All right. Plug it in there. And as you guys know, I've talked about this before, when you're doing order of operations, okay, because of the fact that I plugged the negative 3 into the second term there on that side of the equal sign, and since that term's negative, remember to think of this as plus negative 2 times whatever you plugged in. Plus negative 2 times whatever you plugged in. So this is plus negative 2 times negative 3. Negative 2 times negative 3 is 6. Since 6 is positive, we put a plus right there. Okay, because it's plus whatever the multiplication is equal to. Negative 2 times negative 3 is equal to 6, so it's plus 6. If it had been negative 6, then you would say minus 6, because that's the same thing as plus negative 6. All right, I know I've talked about that a lot, but it's just such an easy thing to make a mistake on. I just want to make sure everybody's okay. Next, obviously we just add that, right? Okay, to get that answer. So what's the final answer here, now that I have figured out both x and y? Writing it as an ordered pair, always putting the x first, because x's always go first in an ordered pair. That is your answer and your only answer, okay? That means that if I were to graph these two lines right here, and again, we're not going to do that, but I'm just saying, if we graph these two lines, then this point right here on the graph would be where those two lines intersect each other, okay? Because the intersection point is where the answer to the system is when you're solving it, okay? That's where it's located when you're solving a system, okay? Now, here's the thing, though, about graphing, though, as we move on to the next problem. Sometimes, you guys, when you are doing a system and you've got these two things that could be graphed, okay, sometimes you get two lines that are parallel. And what's the problem with that compared to this situation over here? The problem is that parallel lines never what? They never intersect, do they? Never. Okay? And because they never intersect, okay, how can you have an answer? Well, the answer is there is no answer when they're parallel. Okay? There is no answer. And so we're going to run into that situation, not necessarily on the next problem, but we will sometimes. So, and what we would say in that case is we would say no solution. Okay? Now, again, because we're not going to be graphing these problems, there's going to be a different way to recognize that. Okay, it'll be something that you're familiar with, and we'll review that carefully. But no solution is a possibility here in these problems. One other possibility, which we are going to run into on this next problem, is that suppose I have two lines or two equations, but then when I graph them, they both end up being the same line. In other words, let's say I graphed the first one here and it looked like that. And then let's say I graphed the second equation there and the second equation was right on top of it. It just lands right on top of the first one. Okay? It's the same line, one right on top of the other. Okay, and I know the equations look different, but that does not mean that they can't be the same line. It is possible to be the same line, even if they are different looking equations. But how many intersection points do you have when you have one line sitting right on top of another one? Every single point is an intersection point, isn't it? Okay. Every single point. So we're going to need to learn about how to express that answer as well. We'll go over that carefully here in this next problem. But these are the three possibilities that you have. You could either have one answer, you could have no answers because there's no intersection points, or you can have a whole bunch of intersection points. Okay? In fact, every single point on the line is an intersection point. Okay? So we'll get into that in a little bit more detail here once I get through this next problem, and we have to write down the answer, okay, because there's a certain way that we need to write this out. We don't just say, hey, the answer is a whole bunch of points, okay? We got to be more detailed than that. So we'll do that. Okay, so let's go ahead and take a look at problem C. Again, you can see here that out of these four variables, the easiest one to get by itself is going to be this one right here because it has a coefficient of 1. Like I said, in the substitution method, a coefficient of 1 or a coefficient of -1, like right here, those are the best ones to pick here on the first step. Again, and I know this always comes from the first equation. That's not necessarily always going to happen. It just happens on these three problems that it came from the first equation in that first step. Just a coincidence, though. It could sometimes come from the second equation. Now, how do I get that variable y by itself there? Just like what we've done in the last couple problems, we need to get we need to move over the other term that is on the same side as the y term. We know that there's two separate terms there because of the plus that's in between them here. And so that tells us that the 6x needs to be moved over to get the y term by itself. But we don't need to divide out after that like we normally would in a lot of other situations, including in the last problem in here where we had to divide by -1. Since the coefficient is +1, you don't need to divide out. If I did divide by +1, it's not going to change anything, and that's why we don't need to do it. The answer would still be -6 minus 6x. So we got the variable by itself. We chose a variable, we got it by itself. That's step 1. Step 2 is to what? It's to plug in that result from step 1 into the other equations. Again, since this came from the first equation, we are going to plug it into the second equation. All right, so let's do that. Since we solve for y, I'm going to replace the y. Okay, I'm going to replace the y with -6 minus 6x. -6 minus 6x. All right. The rest of the equation there stays the same. All right, and then you solve that resulting one variable equation that you now have. All right, but something interesting is going to happen when we do that, but don't worry, we'll go over that carefully here. Let's just proceed as we normally would here. Distribute first. When you solve a one variable linear equation from chapter 3, all right, we distribute first, we then combine like terms, but what happens when we combine like terms right here? The x terms completely cancel out, and we get this right here. Does that look familiar to you guys? I hope it does, because we talked about something similar to this back in chapter 3 when we were solving the one variable linear equations. If the variables disappear completely and you get a true statement, 22 and 22 truly are equal to each other, so it's true. When that happens, we just stop right there and we said that the answer was all real numbers. If it had been false, like something like this, that's when it's no solution. That's the situation where you'd have parallel lines, you guys. Okay, that I was showing you in that graphing illustration a few minutes ago. We won't worry about that yet. Let's look at when it's true, though. All right, when it's true, it says all real numbers. But that's not quite how we're going to write the answer this time. And the reason why is because, remember, you guys, even though the equation that I'm solving right now in this current problem, even though it's the same kind of equation we saw in this chapter 3 section, all right, when we had all real numbers. The fact is that what we're ultimately trying to solve here is this system of equations with two variables in it. Okay, this is just a part of the problem. The entire problem that we're trying to solve is this thing up here. And it's got two variables and it's got two equations as well. And so it's not going to be all real numbers, but it's going to be similar to that. Okay? Anytime you get this result right here where the variables disappear in a system of equations, okay, the variables disappear and you get a true statement, all right, it's going to be this situation right here that I just talked about where it's going to be the same line, one line right on top of the other. And there's an infinite amount of intersection points there. So the answer is going to be an infinite number of solutions, but what solutions are they? You might be wondering to yourself, can I just say all points or all ordered pairs? Is that okay to say that? No, that wouldn't be okay to say that because that would be implying that every single ordered pair on an entire x-axis, y-axis grid, every single point everywhere, okay, would be a solution. That's not true. The intersection points are just on the line. So there is an infinite amount of solutions, but it's not every single point on the entire grid. So what is it? Again, it's all the points on the line. How do we express that mathematically? We can't just say, hey, it's all the points on the line, even though that's true. All right, we got to be more mathematical than that in how we say the answer. Okay, so here's what you do. I know this is going to look kind of weird, but this is just the way that we do it. We use this fancy looking bracket. Okay, it's a lot of times used for solution sets. And then you put a general looking ordered pair in there, x comma y. Just say x comma y with the commas, just like a normal looking ordered pair, but put x and y in there. With the fancy brackets here, with a slash mark up and down right here. And then what you do after that is you can pick whichever equation you want to put into the answer after that slash mark there. The reason why you can pick is because those two equations represent the same line. And so since they represent the same line, it doesn't matter which one you pick. It's the same thing either way. So I'll go ahead and put the first equation up there. Don't pick one of the equations underneath here, okay? Pick one of the original equations. But either one of those is fine because they represent the same thing. So that's an acceptable answer right there. Since it is okay to pick the other equation, I will just say that you can also do this. You don't have to do both of these answers, just one of these answers with either equation in it from the original problem. So you could do this one as well, but either one is fine. Okay, you could either pick, you could either write it like this with the first equation, or you could write it like this with the second equation. All right, but that's what you do when this is true with no variables. Okay, so let's review here. Usually you're going to get one answer. Okay, the variables will not disappear in that case. You just go through the normal thing we did in the first couple problems, and you'll get your normal, ordered pair at the end with one x value and one y value. Sometimes the variables will disappear. If the variables disappear and you get a true statement, you write it like this. Either way is fine. If you had gotten a false statement, such as, say, for example, 12 equal to 14, okay, or 6 equal to 9, something like that, where the variables disappeared and you just have two numbers that are not equal to each other. In that case, you would say no solution, and then that would be just like this example where you have parallel lines with no intersection points. You'll run into that possible situation in this next set of problems that I'm going to ask you to do here. Speaking of that, please look at the second page right here. You'll see that there's 4 problems. One of these 4 problems will have that situation here where you got to write the answer like this, where it's true with no variables. And then there will be one problem where it is no solution, where you'll see the variables disappear and it'll be a false statement. The other 2 problems will be the normal looking answer with the ordered pair. Okay. Notice in this problem right here, by the way, just to let you know, see how x is already by itself right here? So step 1 is already done for you here, all right? Since x is by itself, just go ahead and take that equation and plug it into the other equation. Remember, since wherever you get the variable by itself in the first step, whatever equation that came from, always plug it into the other equation. So this equation will get plugged into this one up here, all right? So just wanted to give you a heads up on that. So please try 1 through 4, hit the play button after that, and we'll wrap up this section. Okay, problem number 1. As we said, the x is already by itself in the second equation, so we'll use that as our step 1 equation here because, again, the goal in step 1 is to get a variable by itself, okay, so that it's also not on the other side, and the x is not on the other side, so we're good there. So we'll use that equation. Since it is the second equation, we'll then plug it into the first equation on step 2, okay. So I did that here. Okay, I plugged the y plus 7 into here, since it's equal to x, and you get this right here. We then have a one variable equation, so we solve that. It will always be linear. It'll never be quadratic if you do it correctly. So you know how to do. You just have to use the linear steps. Okay, distribute, combine like terms, 3y plus 14. Move over the 14 with the 4. All right. And then you need to divide out, and you get y equal to -6. That's step 3. Step 4 is to then combine together step 1 and step 3, right? Like we said, you take the answer from step 3 and you plug it into the result you got from step 1, the equation that you got with the variable by itself. Okay, make sure to plug it into the correct variable. Since y is equal to -6 and not x equal to -6, it's y equal to -6. We plug it into the y here, and it gives us this right here. -6 plus 7 is equal to 1. And so therefore, you now know what both variables are equal to. You put them together as an ordered pair. X always comes first. And that is problem number 1. Problem number 2. Which of those 4 variables is easiest to get by itself? Well, you definitely don't want to pick the x's because they have coefficients that are not going to be nice. They're going to give us fractions. We don't want that. Okay, these 2 variables, though, have -1 and 1. Those are both fine. But 1 is actually easier than -1 because you don't need to divide out. You could do this one. That's okay. If you did it, you should still end up with the same correct answer if you do everything correct. But this one is easier, that's all. So I went ahead and did that. I went ahead and moved over the 3x with the 21 to get the y term by itself. But then once I got the y term by itself, because the coefficient is +1, you don't need to divide out. And so you already have your variable by itself. We then plug that result. Since it came from the second equation, we plug it into the first equation, always plugging it into the other equation on step 2. And so I plugged it into here, replace the variable with the parenthesis, and then put the appropriate thing that y is equal to inside of there, which is 21 minus 3x. Make sure that this minus here stays outside of the parenthesis. Only the parenthesis only replaces the variable, not anything outside of it. So the minus should remain outside, the one that's originally in front of the y there. We then solve that equation. We distribute out the invisible -1 in front of the parenthesis there. All right, and then we combine like terms, 5x. We then move over the 21 with the 4. We divide out, and we ultimately get x equal to 5. So they then combine together step 3 and step 1 by taking the result from step 3, 5, and combining it with the equation we found at the end of step 1. Here it is right here. And we plug in the 5 into the x there. So we get y is equal to 21 minus 3 times 5. And then you then figure out what that is equal to on the other side of the variable. Okay. And so we get what here? Y equal to 6. You put those two answers together, 5 and 6, okay, is your final answer there. Okay. Number 3. Okay, number 3. What do we got to do here in number 3? Again, you can see here that out of the 4 variables, this one is clearly the easiest one to get by itself because it has a coefficient of 1. All the other ones are not good because they're all going to create fractions if you divide by 4, or if you divide by 12, or if you divide by 3. Okay, so let's use the second equation here, and let's get that x by itself by moving the 3y over with the 6. I did that, and x is already by itself. You don't need to divide out because the coefficient is 1. All right. All right, and then we what? Then we take that result from step 1 and we always plug it into the other equation. Since step 1 came from the second equation, we got to plug in the result of step 1 into the first equation. I did that here. Okay, and it leads to this equation. We then solve that equation with the normal linear equation steps. When you have a one variable linear equation, I distributed. But then when I combine like terms, the variables went away, didn't they? And you get 24 equal to 24. What did we say about when the variables disappear and you get a true statement? We said that it's going to be this type of result right here. You could write it either way. Again, you do not have to write both of these things that I circled, just one or the other. They both mean exactly the same thing. Okay, I'm just giving you your options here. You could do either one. All right, so but that's what happens when the variables disappear and it's true. Okay, you write this thing out and you put either the first equation or the second equation inside of these fancy looking brackets on the right hand side of the slash mark. By the way, what this means, you might be wondering, what does all this mean? Why do we got to write all this? This means by definition the set of all ordered pairs, and then the slash mark means such that. So it means the set of all ordered pairs such that 4x plus 12y is equal to 24. Okay, that's another way of saying, hey, what are all the solutions to this equation? Because all of the solutions to that equation are all of the points on the line when you have the same line. And this problem is one of those problems where it's one line right on top of the other. All of the intersection points are on the line. Okay, so all the points on the line are going to be a solution. All of the ordered pairs that make this true, in other words, all the points that are solutions to this equation are going to be the final answer to this problem. And that's why we write this out like that. Okay, it actually means what it's supposed to mean. It's all of the solutions to the entire line because all of those points on the line are intersection points. Problem number 4. Again, the negative y right here is the easiest one to get by itself because it has a coefficient of negative 1. So I moved the 2x over, but I still got to divide out by negative 1 to get the y completely by itself. Remember we said in problem B on the front that when you divide two terms by negative 1 like that, all it does is just change the signs of those two terms. All right, you get positive divided by negative is negative, so we put the minus in front, and then it's just 7 and 1. Negative divided by negative, though, is what? That is positive, so I put a plus in front of that, and then you got 2x over 1. Remember, you should have no signs inside of your fractions on the top and bottom. Okay, the signs, the result of the signs go in front of the fraction, not inside. All right, so when you divide, okay, your signs, if it's negative, you put a minus in front. If it's positive, you put a plus in front. But the ones don't mean anything, do they? All right, like we said in problem B. Negative 7 over 1 is just the same thing as negative 7 only. 2x plus 2x divided by 1 is the same thing as just plus 2x. And so the fractions go away. You don't need to write down the step here, right? By the way, I know you're probably thinking, hey, do I need to write down those ones? We already know they don't mean anything, okay? No, as long as you're sure you're writing this correctly here, you can go ahead and skip this step over here. That's fine. I just want to make sure you understand why the fractions disappeared. So then we plug that result from step 1 into the other equation. Since that came from the first equation up here, we plug it into the second. So I plugged it in, all right, into the y. Since y is equal to negative 7 plus 2x, the y gets replaced by negative 7 plus 2x. I then solve that equation by distributing. And then once again, when I combine like terms, the variable terms completely cancel each other out. But this time, after the variables disappeared, instead of getting a true statement like I did over here, I'm now getting a false one. So when the variables disappear and you get a false statement, what did we say about that? We said that the lines were going to be parallel, okay? And you don't need to say that in your answer, okay? You don't need to talk about the graphs in the answer. Again, the graphs are just to help you understand the answers better. But what do we need to say when they're parallel lines? No solution, because there's no intersection points. So once again, when you get a situation where the variables disappear, but it's a false answer, a false statement after the variables disappear, these two numbers are not equal to each other. That's why it's false. That leads to no solution. Okay? So 3 different possibilities here when you solve these systems. Usually you'll get just one ordered pair as your answer, but sometimes you'll get either this type of answer here or this one here. Now in the next section that we do in the next video, we will also have these same 3 types of answers. It's just that the method that we use to get to the answer is different. It'll be a different method, but the results will be similar. Okay, so we'll see you back here for that. That is section 5.3. In the meantime, have a great day and take care.